So what I was just trying to recall and saying that if you want to test the fact that beta 1 is 0 or not, under the null hypothesis, this statistic has a distribution, T-1 distribution. So one can, it just now involves in computing the probability of observing any number equal to mod T or larger than absolute value, right? So what you do is to test beta 1 is equal to 0. So what we will do is we will just compute the probability that Tn minus 1 is bigger than mod T. What's the chance of getting this number in absolute value? So mod Tn minus 1 is bigger than mod T. You want to compute this, and this is what's called the p-value. This is what you will do. And then if p-value is small, you will reject the null hypothesis. P-value is large, you will not have evidence to reject the hypothesis. That's that. So the p-value indicates. So the p-value indicates let's say a small p-value. A small p-value indicates that it is unlikely to observe a substantial association between X and Y. Need to observe a substantial association between X and Y. So that's how you would have, you see this evidence of rejecting null hypothesis. So you reject the null hypothesis. That's what you do in testing. So now let's say once testing has been done, is there a way to assess the accuracy of the model? Okay, so testing tells you if beta 1 is 0 or beta 0. That means that tells you the relationship between X and Y. So is there a way to assess the accuracy of the model? So how does one assess the model? So let's write this down. Next question is how to assess the model. Like is the linear model the correct thing to do or not? Right? So that's one thing you have to understand. How does one do this? So there are two ways to do this. So one way is by what's called the residual standard error. Okay, so the quality of a linear regression. So the quality of a linear regression right is assessed by two quantities. One is the residual standard error, and the other is called the R-square statistic. So it is assessed by two quantities. One is the residual standard error, called the RSE. I'll explain that in a second. The other is the R-square statistic. The two things that one can use. So I will try and show both of them in a second. So so let's discuss one by one. Okay. So the R-square statistic is essentially, so we already know what the residual sum of squares is. There's RSS is this residual sum of squares right here, right? We did this a little before. This is the residual sum of squares. This is RSS. So it's summation of yi minus beta. Let's copy this down. So write the answer. I'll write the RSE down. So the RSE is following. That is the residual standard error, right? Is what is going to be equal to. So first we know what the residual sum of squares is this, and the RSE is given by. It's just a standardization, like square root of 1 over n minus 2 into RSS. that's defined as the residual standard error. So what is it? If you think a little bit in statistics, if you've seen this thing before, this is just an estimate of sigma. Right? This is an estimate of sigma. So if you did not know sigma, this is one way of estimating sigma. You take the root mean RSS and take the square root. Because what is RSS essentially? RSS essentially involves taking the yi's minus the predictive value of the yi's, right? So RSS was yi minus yi hat the whole square. That's what RSS was. So that's like, so this essentially is going to be equal to, equal to the square root of 1 over n minus 2. And you can think of it as the sum of I equal to 1 to n of yi minus the estimate. What is the estimate? Estimate is beta naught hat minus beta 1 hat times xi, right? The whole square. So in some sense, you're estimating the standard error of y or sigma or the error term that you have in the model. So the RSE is one way of assessing, is considered as a measure of lack of fit of the model data. Right? So if the predictions are very, very close, that is yi is close to yi hat, right? If this is small, then RSE will be very small. Then we can conclude the model fits the data very well. If yi is very, very far from the predicted values, then we'll say RSE is very large, the model is not predicted. So let's write this down. So if yi is close to, let's say, beta naught hat minus beta 1 hat xi, if this is close, then this will imply RSE is small. And that gives you the fact that it prescribes the model might fit the data. So the model fits the data. Next thing we can go and say is that if, let's say, yi's are very, very far from beta naught hat minus beta 1 hat xi, that is, they are not close to, they are either very small or very large from the predicted value, then what will happen is it will result in RSE being large. And you will say the model doesn't fit the data. This is not true. It is not true. Here, this is true. The model fits the data, and here it's not. The model does not fit the data. So RSE will give you a gut feel of with the. So RSE kind of gives you an absolute measure of lack of fit of the data. So RSE provides an absolute measure of lack of fit of the data. That's what RSE will, right? That's what RSE does. But it's measured in units of y. That's one thing you must keep in mind. It's measured in units of y. So it's measured in units of y. So it's measured in units of y. And it's not quite clear what constitutes a good RSE. So then there's another thing called the R-square statistics. Let's discuss that. So another statistic is called the R-square statistic. R-square statistic. So here what we do is we take, we did this long time back, total sum of squares. Right? This is yi minus y bar the whole square. So you took at the total sum of squares, we know, is going to be summation I equal to 1 to n of yi minus y bar the whole square. Right? Total sum of square. And RSS, we know what it is. So the R-square statistics is essentially defined as the total sum of squares minus the residual sum of squares, the whole thing by RSS. So it's equal to 1 minus, but TSS. Is 1 minus the residual sum of square divided by total sum of squares. So how is it going to help? So first observation is that the total sum of squares is what? What is it doing? It's measuring the variance of y. Measures the variance of y. That's what TSS is doing, right? So it's some measure of the variance of y. What is RSS doing? RSS is measuring the amount of variability that's left explained after performing the estimation, right? So what is RSS doing? RSS is doing, RSS is what? RSS is y minus the predicted value, right? Y minus the predicted value. So RSS is measuring measures the variability that is left unexplained after fitting the model. Measures the variability, let's say for lack of a better word, I'll just say that is not explained post fitting the model. Post fit from the model. That's what RSS is doing. So TSS minus RSS, what does it measure? It measures the amount of variability in the response that is explained or removed by performing the fit. Right? TSS, total sum of squares minus RSS. What does it measure? It measures the amount of variability in the data that is explained by fitting. Right? So it measures the amount of variability right, in the data that is explained by fitting. Right? In the data y that is explained by the regression line, by performing the fitting, performing these squares, performing these squares. So what TSS minus RSS. Then what is R squared doing? R squared is doing 1 minus RSS by TSS, or TSS minus RSS by RSS. Right? So R squared statistic measures the proportional variability that can be explained by using X. Right? So R squared measures, what does R squared measures now? R squared measures the proportional variability that can be measured, measures the proportional variability in Y that can be explained by X. The proportional of variability in Y that can be explained by X. Very nice. Maybe not by X, by using X. So that's what these quantities exactly mean, the RSS and R squared statistic, right? So it means if an R squared statistic is close to 1, that means a large proportion of variability in Y is explained by the fit. And a number near 0 means that it's not the case. It means there's something wrong with it. If this is close to 1, that means you are doing a good job. Your line is explaining the variability of Y as compared to the true variability. That means so R squared is 1. If R squared is close to 1, then indicates what? A large proportion of variability is explained by the model. Right? It means that large proportion of variability is explained by the model. And R squared is close to 0 means that this is not true. And it's not, the model is not a good fit. That means that the linear model is perhaps wrong. Very nice. So unlike the RSE, the R-square has the advantage, it's always between 0 and 1, the way it's defined. But it can be still challenging. What's a good R-square statistic? If it's very, very close to 1, it's okay. If it's not very close to 1, how does one do this? In applications, it's always a constant tussle between a result standard error and the R-square statistic. If you think a little bit, the R-squared is actually a measure of the correlation. If you just think a little bit, if you just write this down properly, R-squared is just a measure of the correlation between X and Y.